Cubical Agda.
Thank you. So this is work together with Changji Xu from LMU Munich and Neil Ghani. So this is a talk about trees. So if you have the time, I would recommend you to go to the city park and look at the nice trees in this city. So it's also talk about ordinals, also known as trees. So classically, this is one of the many definitions of what an ordinal is. So it's a transitive set such that every non-empty subset has a least element according to the membership relation. And obviously, this is not a good constructive definition, because you can't even prove that 2 is an ordinal with this definition. But if we ignore that and we take our constructive hat off for the time being, with the goal of this work to put it back on in some sense, then we can think of some ordinals. So all the finite numbers considered as von Neumann ordinals, so containing all the smaller numbers, can be proven to be ordinals. Omega is a fancy word for the natural numbers. It can also be seen to be an ordinal. Ordinals are closed under addition, which means you put one before the other. So these things are considered to be greater than these ones. The closed under multiplication, so you can take exponents. And we also have the ordinal, which is normally known as epsilon 0, which is the least ordinal such that it's a fixed point of the omega to the operation. And because using this definition, membership becomes a strict total order, so we often just write less than instead of membership, just trying to stay away from the set theory as much as possible. And an important property of this order is that it cannot be an infinitely descending sequence of ordinals. So if you have a sequence of ordinals, at some point you must stop. Right? And already one of the first papers about program verification by Turing used this to prove termination of programs. And the idea is that you assign an ordinal to each recursive call of your function, and then that means, because of this property, that means that you can't have infinitely many recursive calls, which means that you must terminate infinitely many steps. Right? And there's been quite a lot of work on representing ordinals in theorem provers, which is something, of course, you need to do if you want to internalize this reasoning and actually prove termination inside your theorem prover. So one motivation for this work is trying to get a nice representation of ordinals that you can use in a theorem prover, so that, for example, if you wanted to, you could mechanize such termination proofs. But I'm not actually touching the termination proofs here. I just want to have a nice representation of ordinals. And the way I'm going to get there is using this fact about the so-called Cantor normal form of ordinals, which says that every ordinal can be uniquely written as a sum of powers of omega. And the important thing is that these exponents can be given in a decreasing manner. So here I'm using less than or equal to. There's also a variant where this is strictly less than, but this is the one I would like to use now. And what's important about the reason I mentioned epsilon 0 earlier is that if alpha is smaller than epsilon 0, just this least fixed point of the omega to the power operation, then all of these exponents are in turn smaller than alpha. So you see that if you take alpha to be epsilon 0, then that's not the case, because you can immediately take beta 1 to be epsilon 0, and you solve this equation. Right? It was a fixed point. But if alpha is smaller than epsilon 0, then all the exponents are going to be smaller again. So if I now take this exponent and I find its Cantor normal form like this, then I'm going to get a decreasing sequence of ordinals, which then must terminate by this property of ordinals. Right? So what I get is a finite representation of this infinite object. Right? I just do this finitely many times, and then in the end I have a finite representation which uniquely determines the ordinal I had, which could be something large. So I want to use this idea to give a fine little simple notation for ordinals. And of course, this only works for ordinals below epsilon 0, because otherwise this might not terminate. Right? So when you want to go beyond epsilon 0, you have to do something more clever. But for now, I'm happy to not be clever and just stay down in the low reaches of the ordinals. So how do you do it? Well, you say that it's either 0, which corresponds to the empty sum, right? Or it's represented by the first exponent and then the rest of the ordinals, right? And this is really simple. This is just binary trees, right? There's a base case, and I have 2 more ordinals that represent these 2 things. So I can represent ordinals just by binary trees. But if I do this, then I've, of course, lost the uniqueness of the representation. Because, for example, It's a well-known fact of ordinal addition that 1 plus omega equals omega. So I have 2 representatives for omega if I just use binary trees. So what I would like to do is to somehow recover the faithfulness of the representation. So not have multiple representations of the same thing. Right? And we do this by using some nice type theoretic features that you can do in the cubical Agda, for example. And we do this in 3 different ways, actually. So one approach using subsets, one approach using mutual definitions, and one approach using higher inductive types that we just had a nice introduction to. Right. OK, so why should you care about this? Well, one reason to care is that these unique representatives makes the ordinals actually behave the way you expect them to behave. Whereas the binary trees, they're just syntax. And there might be some properties of ordinals that you expect, but you don't have them unless you have these unique representatives. That's why I want to have a faithful representation. And why do I want to do this in cubical Agda? Well, I want to have univalence and higher inductive type that computes. Because I don't want my computations to get stuck. I actually want to have canonical terms in the end. So that's why I want to do this in cubical Agda. OK, so let's look at the first approach, where we look at the subsets. So here we start with just defining the trees. This is what we said was not a good thing to do, right? So that's why we're going to take a subset of the well-behaved trees. And we see that this is the same definition that we had before, except that I use this fancy mixed fixed notation of Agda to make a suggestive name for the constructor. So base case and node case, where I have 2 more trees. OK, so that's not quite good. I want to single out the trees that are actually in Cantor normal form. Right. So I'm saying that 0 is already in Cantor normal form. And if A is in Cantor normal form, B is in Cantor normal form, and if A is greater or equal to the first exponent of B, then this omega to the A plus B is also in Cantor normal form. Right. So this was an inductive definition. This is an inductive family. And of course, this is using this greater than relation, which I haven't told you what it is. It's not complicated, but it's maybe not 17-minute material. And it's also using this first function, which just gives you the first exponent. So first of 0 is 0, and first of something non-zero is the first exponent, as you expect. Right. OK, so we can define this predicate, and then we can form the type of ordinals as a sigma type of a tree together with a proof that it is in Cantor normal form. Right. So we don't consider all the trees, we just consider the subset of the ones that are well behaved. And I'm justified to call this a subset because you can prove that this predicate is actually proof relevant. That is, it's in hot speak propositional. That is, I can prove that any 2 elements are actually equal in this. So there's no data there's not more than one proof of this. So equality of ordinals here is just equality of trees. Right? There's no equality in the proofs. So the nice thing about this representation is that I'm not really using any fancy features. Right? I'm using sigma types, I'm using inductive families, but you can do this. You could have done this 10 years ago in any proof assistant you wanted based on type theory. The con of this is that there is a lot of junk terms throwing around, right? Not when I'm in the sigma type, but all the time I always have to rule out the impossible cases by saying, well, actually that thing can't have been in Cantor normal form, so I'm going to go away and prove a lemma that this is an impossible case. Right? So I have all these junk cases that I don't want to consider. And I also have to do a lot of code duplication because I typically define an operation on my trees, and then afterwards I have to go through the same steps again to prove that this is actually in Cantor normal form. Right? And doing this is not completely trivial because the lemma that you need is usually not directly proving that it's in Cantor normal form. It's something to do with the order. So you have to come up with these lemmas yourself. So wouldn't it be nice if you could not have these junk terms and not have this code duplication? And it turns out that nowadays we can. So by using mutual definitions, we can get this by construction instead, that every term is in Cantor normal form. And the idea is it's not so complicated, I think. So instead of first defining the trees and then the order in the first function, we're defining everything at the same time. So you can do this in Agda with a mutual definition. And the point is that then, so this is formally called an inductive recursive definition, because these two things are defined inductively, and this is defined recursively. And the idea is that we have the same definition as before, so we have a base case, and we have a step case where we have two subtrees, but now we also ask for a proof up front that A is actually greater than or equal to the first exponent of B. Right? So we can do this because we are also defining these things at the same time. And then again, you define the order in the same way, which I'm still not telling you how it is, and the first function in the same way again. Right? But the point is that now there are no junk terms anymore, because any term of this type you can form always comes with a proof that has the counter-normal formulas in it. Right? And again, you can prove that this order is proof irrelevant, and something that's nice is that you can prove that it's actually a trichotomy. So you can, given two ordinals, you can decide if A is less than B, or if A is greater than or equal to B. Right? So this is something that's nice, because you wouldn't expect this from the real ordinal, so to speak. But here we have a nice notation system for it, so we can actually look at the syntax and decide which one is which. And this is a real disjunction. So if you can pattern match on this and see which case you're in. Right? It's not one of these fancy cubical hidden merely disjunctions. And using this trichotomy, you can define the usual operations, so plus and times, and exponentiation if you want. And you can prove properties of these things. It's not so hard. Associativity, distributivity, etc. And when you do this, you still have to prove some lemmas about the order, but they are kind of popping out for free from the proof obligations that you have. So you get some, the lemmas are suggesting themselves because you have to prove everything at the same time. You can also prove that these things in some sense really are ordinals. So you have transfinite induction. So if you want to prove a property of one of these, then it's enough to prove it, assuming that you already know it for everything that's smaller. And this is something you can't prove if you don't have this unique representation. So here's where you get something back from insisting on a faithful representation. Okay, so that's one way to do it. But so far, I haven't actually used anything that's cubical in this. Right? I used something that's Agda, because I have these nice mutual definitions, but I haven't used any cubical features. So here's another approach, where we try to force things to be the way that we want them to be, more or less. So we want to avoid this redundant representation. Right? And with the mutual approach, we require that to be given in a certain order. But another option would be to just quotient out the difference. Right? So say that it doesn't matter if you give beta 1 and then beta 2, or beta 2 and then beta 1. But that means that this plus I've used here can't be the ordinary plus, because plus of ordinals is not commutative. Right? So this must be some other operation. But the point is that cubical Agda, with the higher inductive types that we got such a nice introduction to 15 minutes ago, allows to have these path constructors as well. Right? Higher inductive types. Okay, I think we can maybe skip what a higher inductive type is, because now we all know it. It's sound because of the cubical sets model. And here is the definition. So we have the same thing as before. We have a base case. We have omega to the something plus something. But we also have a path constructor which says that you can swap the first two exponents here. So omega to the a plus omega to the b plus c is the same as omega to the b, and then a and then c. So swap the first two exponents. Right? And then I'm also made sure that this is actually a set in the sense of homotopy type theory. So all equality proofs are equal, just to make it not too high. And if you pattern match on this, we also had something like this in the last talk. You must show that you give the same thing, you respect the swap function. So here is what swap says is equal to this. So that means whenever you define a function, you also have to give the same result on the swapped things. Right? So that means that it's easy to define commutative operations on this. It's not so easy to define non-commutative operations. But there is a version of arithmetic which is commutative for ordinals, which is not so well known, perhaps. So this is called Hessenberg arithmetic. And here is how you define it in cubical Agda. So you're given x and y, we pattern match on x, and then I have to give these cases. Well, 0 plus y is still y. In this case, we just keep the first exponent and continue adding. And then here we have to show that we give the same result if we swap, but this is another instance of swap. And truncation is similarly quite easy. And then you can prove that this is commutative. So this is easy to define on this representation, but quite hard to define on the other representation. Okay, so which one is better? And the answer is all of them. So I've kind of spoiled this in the title of the paper, which says that they're all equivalent. Right? But I do want to stress this, that depending on what you want to do, the mutual approach might be much easier to work with, or the hit version might be much easier to work with. Right? And then what you do, you prove that they are equivalent, which by univalence means that they are equal, which means that you can actually transport operations between the different representations. Right? So how does the proof work? So it's not so hard to see that these two are equal, the subset version and the mutual version. This one is a little bit more fun. So to get a function from the mutual version to the quotient one, you just forget about the order. To go the other way is the fun part. And what you do is basically insertion sort. So you have your exponents, and you have to make them in the right order. And that's exactly what insertion sort does. Okay, and then once you've done this, you can use univalence to transport things between them. So you can get an order on the hit version using transport. You can get a commutative plus on the mutual version, which is not at all easy to define directly. And because you're in cubical Agda, all of this computes. Right? So you see here I have a proof that one Hessenberg sum omega is omega plus 1, and the proof is REFL. This just is definitionally true, right? Which wouldn't be true in a system that's not cubical Agda. Okay, so I think you can have a lot of fun using these new features of type theory to do even down-to-earth things that are not so synthetic homotopy theory oriented. So here I've used it to represent ordinals below epsilon 0. You can look at the Agda formalization. And one moral of the story is that you should define the operations on the right data types, because that's going to make your life much easier. Right? And there's some future work. Okay, thank you very much.
Are there any questions?
So you can kind of explore this encoding space for a lot of things. Do you think your conclusions carry over, or should we keep exploring this all three options every time we have to do something like this?
I guess the short answer is yes, that makes sense. I don't think there is always a best option. So I mean, we know this even before we had higher inductive types and things like this. When the search space was smaller, there's not one good data representation. Depends on what you want to do. Right?
Okay, thank you.
Any other questions?
Does showing that the mutual and the hit representation are equivalent already rely on the univalence axiom, or is that not using univalence?
So to show that they're equivalent is not using univalence.
Ah.
It's just a step to go to the identity.
Okay, to get the equality.
Yeah.
Okay, let's thank the speaker again.